If the universe were contracting, would time feel like it's running backward? That's still a favorite thought experiment among physicists. It's worth noting, though, that several arrows, entropy, memory, causality, and the expansion of the cosmos all point the same way. That alignment is reassuring. It suggests time isn't just a trick of perception, but something embedded deeply in the workings of reality, shaped by energy flow, increasing disorder, and the slow, steady unfolding of everything from a once very orderly start. But not everyone agrees that time, as we experience it, is truly fundamental. Some physicists argue that the arrow of time is something that emerges only when complex observers like us watch simpler systems like tea cooling or eggs breaking. In certain interpretations of quantum mechanics, time isn't a force or a flow at all. It's just another label for different states. The universe doesn't feel time, we do, and that's the puzzling part. No matter how far we dig into entropy, probability, or equations, time remains both strikingly real and frustratingly slippery. It's something we move with like a current, yet we can't pause it or see outside it. We don't know what lies ahead. We can't go back. Still, we live by its rhythm, finding comfort in the idea that the future, whatever it holds, is always on its way. So the next time it feels like time is slipping through your fingers, remember, it's not gone. It's simply obeying the one rule it always follows: moving forward, building entropy, and leaving behind a trail of mismatched socks and empty TEACUPS. In classical physics, time behaves like a reliable train schedule, steady, predictable, always on track. In quantum mechanics, it's more like jazz, improvisational, unpredictable, occasionally strange. Just when you think you've got a handle on it, you're handed a cat in a box and asked to decide if it's both alive and dead. Welcome to quantum physics, where reality becomes uncertain and time turns into more of a polite guideline than a fixed law. In classical physics, you can point to something and say, there it is, doing this right now. In the quantum world, particles don't have clear positions or momentum. They exist as probability waves, mathematical clouds of where they might be and what they might be doing. So, where does time fit into that? Surprisingly, time doesn't hold the same spotlight in quantum mechanics as it does in classical physics or general relativity. Instead, it usually appears as a kind of background parameter, something added to equations just to keep the system evolving. Like pressing play on a simulation. Take the Schrödinger equation, the core of non-relativistic quantum mechanics. It describes how a system's wave function, that odd cloud of probability, changes over time. But time in this context doesn't bend or stretch as it does in relativity. It's just there, an unchanging stopwatch in the background, not drawing attention. This leads to a strange divide. Quantum mechanics tracks how states evolve over time, but it doesn't explain what time is. It treats time the way Newton did, fixed and absolute. While space and matter fluctuate unpredictably in front of it, things get even stranger. When we try to combine quantum mechanics with general relativity, the effort known as quantum gravity. These are the two main pillars of modern physics, but they clash in fundamental ways. In general relativity, space-time is flexible. It stretches, bends, and responds to matter and energy. Time isn't fixed. It's part of the universe's structure. But in quantum mechanics, time stays rigid, a kind of universal metronome that doesn't care what's happening. Bringing these two perspectives together is like trying to choreograph ballet using instructions from a heavy metal concert. It leads to what physicists call the problem of time in quantum gravity. When we try to describe the entire universe using quantum theory, space, matter, everything, something odd happens. Time vanishes. One equation that shows up in quantum gravity is the Wheeler-DeWitt equation. It looks a lot like the Schrödinger equation, except it has no time variable. It's completely timeless. There's no past or future, just an endless present. A kind of eternal now. So what's really happening? Is time real? Or is it just something that emerges from how we observe change? Some researchers think time is emergent, not a core feature of the universe, but something that appears only when we zoom out. Like temperature, A single molecule doesn't have a temperature, but trillions of them together do. In the same way, time might arise from the combined behavior of many quantum systems. Others focus on entanglement, the strange quantum link where two particles influence each other instantly, no matter how far apart. Some theories propose that the arrow of time, and perhaps even time itself, could emerge from increasing quantum entanglement. The more interconnected everything becomes, the more time appears to flow. Then there's the many worlds interpretation. In this view, every quantum event, every coin flip, every measurement splits the universe into multiple parallel branches. There's no randomness, just endless branching timelines. In this picture, time isn't a flowing river. It's an enormous, ever-dividing tree. Every choice creates a new branch. Somewhere out there is a version of you who remembered their umbrella this morning. But if time is so uncertain at the quantum level, why does it feel so steady to us? Well, we live in a world where vast numbers of quantum events smooth out into a stable, predictable reality. Our brains, built from trillions of particles and neural signals, are tuned to see cause and effect. We wake up, brush our teeth, eat breakfast, and head to work, hopefully in that order. For us, time is a story, a sequence that helps us make sense of change. And storytelling is something we humans are very good at. We link events into memories. We imagine possible futures. We define our identities through time, past experiences, present choices, and hopes for what's next. Whether or not time is fundamental, we treat it as something real. Still, quantum mechanics reminds us that behind our comforting narrative lies something more subtle. Time may not be the ticking of a clock or the turning of a calendar page, but the unfolding of possibilities, the evolution of probability, reality reshaping itself. Moment by moment. So while your watch may say it's 10 minutes to midnight, quantum physics gently whispers, well, from a certain point of view, time isn't just something we track with clocks or calendars. It's also present in your body, in your cells, your sleep, your hunger, even your moods. Whether you're a night owl, an early riser, or just perpetually tired, your body runs on its own internal clock, and it's an ancient one. This internal timekeeping system, or more precisely a network of them, is known to scientists as the circadian rhythm, from the Latin circadium, meaning about a day. Circadian rhythms are biological cycles that repeat roughly every 24 hours. They regulate everything from when you feel tired to how your body processes food, and they exist in almost all living organisms: humans, animals, plants, fungi, and even some bacteria. If it's alive and somewhat organized, it probably keeps time. At the center of your circadian system is a tiny brain structure called the suprachiasmatic nucleus, or SCN. It's located in the hypothalamus, right above where your optic nerves cross. This strategic placement allows your internal clock to sync with light cues. When your eyes sense morning sunlight, the SCN receives the signal and adjusts various functions, from hormone levels to body temperature. Think of it as your brain's version of hitting snooze on the sun. One of the SCN's most important roles is regulating melatonin, often referred to as the sleep hormone. Melatonin levels rise in the evening, making you feel sleepy and fall in the morning, helping you wake up. It's your body's gentle reminder. Maybe skip that next episode. Whether you follow that advice is another matter. Interestingly, while your circadian rhythm runs close to 24 hours, it's not exact. Most people have a natural rhythm of about 24.2 hours. Left completely to ourselves, say, living in a cave with no clocks, we'd slowly drift out of sync with the actual day. That's where light becomes essential. Exposure to morning. Sunlight resets the clock daily, keeping us in line with Earth's rotation, or at least close enough to catch our alarms. Disrupt this balance, though, and strange things happen. Enter jet lag, humanity's least welcome travel companion. Jet lag occurs when your internal clock is out of sync with your surroundings. If you cross several time zones and hours, your brain might think it's midnight when it's actually noon. Even your digestive and immune systems get confused. That's because different parts of your body adjust at different rates. Your brain may adapt quickly, But your stomach might still think it's snack time in last week's time zone. Artificial light is another modern disruption. Before electric lighting, human activity mostly followed natural light, rising with the sun. Sleeping after sunset. This pattern still exists in communities with little artificial light exposure. Today, however, we're surrounded by screens and lights, especially blue light, which can fool the brain into thinking it's still daytime. This delays melatonin release and shifts our circadian rhythm later. It's not that we're all becoming night owls. It's more like we've invited a glowing owl into the room and handed it the remote. Not everyone's internal clock ticks the same way. Some people are naturally early risers, larks, who feel energetic in the morning. Others are owls, more active and creative at night. These chronotypes are partly genetic, so if you're not a morning person, it's probably not just bad habits. Your brain genuinely isn't ready to be awake. And really, who are we to argue with a billion years of evolution? Circadian rhythms also affect body temperature, which usually dips in the early morning and rises throughout the day, peaking in the late afternoon. That's why athletes and performers often do better later in the day. Their bodies are more alert and running efficiently. On the flip side, this is also why early meetings can feel like solving equations, while still half asleep, but biological time influences more than sleep. And body heat. It shapes your metabolism, immune response, mood, and even how you respond to medication. This has led to the rise of chronopharmacology, the study of how the timing of medicine affects its impact. The same drug might work better in the morning or evening, depending on what it's treating and how your body processes it at that time. Plants also follow circadian patterns. They open their leaves to the sun during the day and close them at night, and even begin preparing for dawn before the first light arrives. This isn't just a response to light, but an internal rhythm that continues even in constant darkness. A sunflower doesn't follow the sun because it sees it. It moves because it remembers. In animals, from birds and bees to rodents, circadian rhythms help guide migration, feeding, and hibernation. Even fungi, living quietly beneath our feet, have internal clocks that regulate when they release spores or grow. All of this suggests that life on Earth is deeply connected to time, not just the kind measured by atomic clocks, but a biological time shaped by light and dark, warmth and cold, hunger and rest. A natural rhythm that pulses through living things like a quiet beat. So next time you feel that 3 p.m. crash or a burst of energy late at night, no, it's not random, it's rhythm. Your body is moving in time with an ancient signal. 1. That kept our ancestors alive and rested long before alarm clocks, calendars, or triple-shot coffees. And while we try to bend time with reminders and routines, deep down, our cells are still quietly tracking the sun. Now, have you ever noticed how time seems to play favorites? A vacation week disappears in a flash while the last 10 minutes of a dull Zoom call drag like molasses. That's psychological time, the way our minds experience time, which often doesn't match what the clock says. Physics tries to describe time as it is. Psychology explores how we feel it. And those are very different things. Let's start with a familiar saying, time flies when you're having fun. This turns out to be true. When we're fully engaged, laughing, immersed in a hobby, or watching something interesting, like, say, a sleepy scientist, we stop tracking time. Our attention is focused, and the brain stops counting seconds. As a result, time seems to disappear. In contrast, boredom stretches time. If you're stuck in line, watching paint dry, or listening to another crypto pitch, your brain becomes hyper-aware of each second. Time seems to slow to a crawl, and every moment feels longer. Then there's retrospective versus prospective time. In the moment, time might feel fast or slow depending on your focus. But looking back, the memory can feel different. If you spend a week hiking in unfamiliar places, the days may fly by, but afterward the trip feels long and full of memories. That's because new experiences create more mental bookmarks. Your brain stores more information, which makes the time seem fuller. Compare that with a routine week. Wake, work, stream, sleep. It might feel slow while it's happening, but later it blurs together. Fewer mental markers mean less perceived. Time has passed. This also explains why time feels faster as we age. When we're young, everything is new. We're constantly learning and forming vivid memories. First bike ride, first heartbreak, first bad haircut. As we grow older, routines settle in. Fewer surprises mean fewer memory bookmarks. Days blend, and years start to fly. Time isn't speeding up, we're just not recording it as actively. Emotions also influence time. When we're scared or anxious, time can feel like it slows down. This has been studied. People who experience intense moments, like bungee jumps or sudden shocks, often report time stretching. One theory is that under stress, the brain captures more detail. When we recall the event, it seems longer because there's more to remember. But during the event, time doesn't actually slow. People don't perform better. They just remember more. So when you say, "That was the longest roller coaster drop ever," the stopwatch says, "Actually, it was 3.2 seconds. Still thrilling, just not superhuman. Then there's attention. Perhaps the strongest influence on psychological time. When we pay close attention to time, like waiting for cookies to bake, we experience each tick of the clock. But when our attention is engaged, absorbed in music, reading, or conversation, time fades into the background. This is closely connected to mindfulness and meditation, which intentionally shift our focus away from time. When we bring attention to the present, a breath, a sound, a physical sensation, time seems to vanish. It's not that we enter a trance or disconnect from reality. Rather, we stop counting moments and simply inhabit them. For many, this brings a sense of relief. You're no longer chasing the next hour, you're fully present in this one. At the more complex end of the spectrum are altered states of consciousness brought on by deep meditation, intense emotion, or certain substances where people report time slowing, speeding up, looping, or disappearing altogether. Some describe timelessness not as a distortion, but as the absence of time, as if they briefly stepped outside the stream and viewed it from the shore. Neurologically, these states may involve reduced activity in the brain's default mode network, a system of interconnected regions linked to self-referential thinking, memory, and time awareness. When this network becomes quiet, our usual sense of identity and time can soften or dissolve. This might explain why moments of flow or stillness often feel deeply meaningful. Children also have a distinct relationship with time. For very young kids, time is fluid, vague, and often irrelevant. Ask a 5-year-old what 5 minutes means, and the answer might be forever or until I finish my snack. As they grow and encounter clocks, routines, and phrases like just a few more minutes, they gradually adopt the adult model of time. Some might argue that this shift is a quiet but real loss of innocence. Then there's anticipation, our brain's internal time machine. Looking forward to something can make time feel slower. Waiting for Friday, for instance, seems to stretch the week. Dreading something can have the same effect. We imagine future scenarios, rehearse conversations, and worry about outcomes, all using the same brain systems we rely on to recall the past. In this way, time becomes elastic, stretched by both hope and fear. So, is psychological time reliable? Not exactly. Is it always rational? Often not. But is it unmistakably human? Absolutely. While we live in a universe governed by atomic clocks and planetary cycles, the time we actually experience, the time that shapes our lives, is constructed from memory, emotion, focus, and imagination. It's time felt, not merely measured. And perhaps that's what makes it feel so personal, so unpredictable, and sometimes so strange. Of course, no conversation about time is quite complete without the question that's inspired endless science. Fiction, philosophical debates, and more than a few awkward dinner party detours. Can we travel through time? Possibly, but it's complicated. Time travel, at least in theory, isn't ruled out by modern physics. In fact, Einstein's theory of general relativity suggests that space-time is flexible. It can stretch, bend, and under extreme and highly unusual conditions even curve back on itself. If that's true, then jumping forward or backward in time may not be entirely off the table. Let's start with the simpler case, traveling into the future. This one isn't just possible, it's already been observed. Enter time dilation, a consequence of Einstein's special relativity. If you travel at speeds close to the speed of light, time slows down for you compared to someone standing still. Zoom around the galaxy in a fast spaceship and return to Earth, and you'll have aged much less than those who stayed behind. Congratulations, you've traveled into the future. No need for a flux capacitor. This isn't just theory. Astronauts aboard the International Space Station experience a very small amount of time dilation. They age just a little less than people. On Earth, the difference is only measurable with atomic clocks, but it confirms the principle. They return microseconds into the future, still in time for lunch. So, future time travel? Confirmed, at least in principle, traveling to the past. Though that's the real challenge. General relativity does permit certain mathematical solutions that could, in theory, allow backward time travel. One example is a closed time-like curva loop in spacetime where an object could return to an earlier point in its own history. Imagine taking a lap around the universe and ending up yesterday. One proposed mechanism for this is the wormhole, a theoretical tunnel linking two distant points in spacetime. If you could accelerate one end of the wormhole to near light speed, and then bring it back, time on that end would lag behind. Step through, and theoretically, you emerge in the past. But there are major hurdles. First, we don't know if wormholes even exist. Second, if they do, they may collapse too quickly to be useful. And third, keeping one open would require negative energy, an exotic form of matter that we haven't figured out how to produce or stabilize. So while wormholes are fascinating in theory, building one is likely beyond our current technology possibly. For centuries, even if backward time travel were possible, it leads directly to paradoxes. The most well-known is the grandfather paradox. If you go back and prevent your grandfather from meeting your grandmother, how could you have been born? To go back in the first place? It's a logical loop that defies resolution. Several ideas try to deal with this. One is the block universe model. All points in time past, present, and future exist simultaneously. Like frames in a movie reel, the entire timeline is already there. In this view, going back in time doesn't change anything. Everything you do was always part of the past. You're simply playing your role in a pre-written scene. Another solution is the many worlds interpretation, borrowed from quantum mechanics. Here, each time you make a change in the past, you create a new branch of the universe. Stop your grandfather from meeting your grandmother, and you create a new timeline where you're never born, but your original timeline remains untouched. No paradoxes, just parallel realities. There's also the Novikov self-consistency principle. This idea states that any actions you take in the past will always be consistent with the future you came from. Try to stop your grandfather, and circumstances will prevent it. Your gun jams, you slip, or he makes an unexpected life choice. The universe, in a way, enforces consistency. Still, all of this remains theoretical. No time machine has ever been built. No time travel has ever been verified. That hasn't stopped speculation, of course. The internet is full of mysterious old photos and curious interviews, but no reliable evidence has emerged. Physicists still debate whether time loops are even possible under the laws of physics. Here's an interesting thought. If backward time travel ever becomes possible, why? Haven't we met time tourists? Shouldn't we see visitors from the future snapping selfies with dinosaurs or attending medieval festivals? One answer is that time travel might only work back to the point the first time machine is built. Others suggest that time travelers are simply very discreet. A more likely explanation? It might just be impossible, and maybe that's not such a bad thing. As tempting as it is to imagine undoing mistakes or revisiting cherished moments, time's one-way flow might be essential to its meaning. We can't revise our lives like a screenplay. We live each moment as it comes, with all its surprises and imperfections. Still, the idea is fun to imagine, and who knows? Maybe someone from the future is reading this right now, nodding thoughtfully, and thinking, yes, the early days of temporal science. If that's the case, welcome. Just don't spoil how it all ends. Now, after discussing ticking clocks, personal perceptions, black holes, and wormholes, we reach one of the strangest questions of all. Does time actually exist? It might sound like a question from a philosophy seminar or a late-night chat over tea, but it's one physicists take seriously. Because when we analyze how we experience time and how we describe it in physics, something unexpected happens. It begins to vanish. Let's start with the familiar view. To most of us, time feels like a flowing river moving steadily from past to present to future. We ride this current, unable to go backward, only forward, sometimes slowly, sometimes quickly, but always in one direction. This perspective is known as presentism, the belief that only the present is real. The past is gone, the future hasn't happened yet, and all that exists is now. It fits with our day-to-day experience, measured out by calendars, clocks, and routines, but there's another view, one made more plausible by Einstein's theory of relativity, eternalism. According to this idea, time doesn't flow at all. Every moment, past, present, and future exists simultaneously. The universe is a four-dimensional block, sometimes called the block universe. In this framework, time is a dimension like space. Your childhood, your retirement, and every moment in between are all fixed in place. You're not moving through time, you're part of it. You don't grow older. You are already older on one page of the book and younger on another. This may sound odd, but it follows naturally from relativity. Consider simultaneity, the idea that whether two events happen at the same time depends on the observer's motion. People moving at different speeds may disagree on what now means. That suggests there's no universal present, no master clock ticking for everyone. That alone challenges our basic idea of time flowing in one direction. Quantum gravity pushes things further. As we noted in earlier chapters, when physicists try to unify quantum mechanics with general relativity, time often drops out of the equations entirely. For instance, the Wheeler-DeWitt equation, used in quantum gravity, doesn't include a time variable at all. According to this perspective, the universe might be fundamentally timeless, but if time doesn't exist at the deepest level, why? Does it feel so real? One possible explanation: emergence. Time, like temperature or sound, may not be a fundamental part of the universe. Instead, it might arise from more basic physical interactions, patterns, relationships, and changes. Just as waves emerge from water molecules or clouds form from air currents, time might emerge from the underlying behavior of quantum systems. Our perception of time may be a mental construction, something our brains generate from observing change. It's like watching a movie. A film is just a series of still images, but when shown quickly, we perceive motion and story. Time, in this view, is the narrative we build from a series of evolving states. Some physicists propose that time might function differently than we think. What we experience as the passage of time could be the brain assembling changes in a fundamentally timeless universe. Enter physicist Julian Barber, who takes the idea a step further. In his view, time doesn't exist, not even as a background variable. Instead, the universe is made up of a vast collection of nows, complete, timeless snapshots of reality. These moments don't evolve or flow, they simply are. According to Barber, our sense of time passing comes from how these nows are organized, and from the memories embedded within them. Picture it as a kind of cosmic photo album with consciousness turning the pages. It's a bold idea, but it raises a thoughtful possibility. Maybe what we perceive as time is simply a feature of how we process the world, not a property of physics itself. After all, humans are storytelling beings. We remember the past, anticipate the future, and organize our experiences using narratives. Time helps us plan, reflect, and make sense of change. It's a practical framework, perhaps, even essential for conscious beings navigating a dynamic world. But that doesn't necessarily mean time is real in the same way a rock is, or a star, or even a piece of cake, which also tends to vanish with the passing of time. Still, not everyone agrees that time is just an illusion. Many physicists argue that even if time arises from more basic physical principles, it still produces consistent, observable effects. Clocks tick, planets revolve, radioactive atoms decay. If we build machines that reliably measure change, and those machines all agree, doesn't that give time some claim to reality? Maybe that's the most reasonable answer. Time is real in the same way stories are real. Not because you can hold it in your hand or trap it in a lab, but because it gives structure to what happens. It's the script that allows events to unfold in a meaningful sequence, even if that script is written in quantum ink on a page we haven't fully translated. So, does time exist? Perhaps not in the way we often assume. It may not be a stream or a ticking mechanism running in the background, but it clearly exists in our experiences, in biology, in culture, and in our scientific models. It shapes how we live, how we remember, and how we plan. It's present in each breath and every bedtime story, and maybe that's enough. Whether time is fundamental or emergent, real or imagined, it gives form to our lives. It reminds us that everything changes, that moments matter, and that somewhere woven into the fabric of existence, you are part of something timeless. And so, dear listener, we reach the end of our small journey, or perhaps just another pause in the continuous loop of moments. Together, we've explored ancient sundials and atomic clocks, followed Einstein's curved space-time, questioned paradoxes, and wondered whether time itself is real. Along the way, we've seen that time isn't a single thing, but many things at once, a rhythm in the body, a product of memory, a twist in gravity, a story told through change. And now, here you are just a little further along your personal timeline than when we began. But how much time has really passed? Seconds? Minutes? An hour? Or did the flow of these words stretch and contract the way time often does when the mind begins to settle? So let me gently ask again, just as I did when we started, where are you listening from tonight? And what time is it right now in your little corner of the world? It's interesting, isn't it? After all this reflection on time being relative, flexible, maybe even illusory, we still find ourselves returning to it, a glowing number on a screen, the quiet hush of night, the familiar sensation of winding down, breath by breath. And if you found even a bit of peace in this quiet journey, if the vastness of the cosmos brought you calm, or if these thoughts helped you drift towards sleep, I'd be truly grateful if you'd like the video, maybe subscribe, or share this restful space with someone who might need it too. Time may be mysterious, fleeting, and possibly not quite what it seems. But right now, in this still moment, it's just you, this voice, and the gentle rhythm of rest. Sleep well, fellow traveler, wherever and whenever you are.